Hello, and welcome to Lecture 2 of Electric Interactions in Phys 1204. In this lecture, we're going to look at how charges move around and differences between conductors and insulators. We've already seen some ways of charging objects. When two objects are rubbed together, they'll often charge each other. For example, we've seen this with a piece of plastic rubbed with a piece of wool. And one thing to notice is that we always need to rub together two objects made of different materials. Another way we've seen, for example with tape, is that if things are stuck together and they get peeled apart quickly, they'll often become charged. In both cases, we have two neutral objects at first, and they become charged by some surface-to-surface interaction with each other. And so we might guess that what's going on here are fairly similar mechanisms. But now let's see a totally different way to charge an object. Here is a ping pong ball covered in aluminum foil, and all I'm doing is demonstrating that it has no effect on these pieces of paper, so it's electrically neutral. So here is that neutral ball, and I'm charging up a plastic rod. And note, as we would expect, the ball is attracted to the rod because the rod is charged and the ball is neutral. However, when I touch the rod to the ball, now the ball is repelled from the rod. Let's see that again in slow motion, and you'll see that the ball jumps away from the rod when it first touches it. So what we've just seen is a totally different way of charging an object from the ways we've seen before. If we have an already charged object and we touch it to a neutral object, then it transfers some of its charge to the neutral object. And so as opposed to rubbing an adhesion, this is a totally different mechanism that we might call charge transfer. But it requires that we already have one object that's charged. For rubbing and adhesion, we started off with two neutral objects, and after they've interacted with each other, they have opposite charges. So this is a process of charge separation. We've started with everything neutral, and we've separated some of the positive out from the negative so that there's a surplus of positive on one object and a surplus of negative on the other object. But charge transfer is totally different. Both objects end up with the same sign of charge, because what's happening is that an object that already has charge gives up some of its charge to the other object. In other words, this is a process of charge spreading out. Our model of charge is intimately tied to our model of how matter is built on the atomic scale. Charge is carried by charged particles inside objects. So all objects are made out of atoms. This is not a picture of an atom. An atom looks nothing like this, but it's a schematic picture, and it shows the structure of an atom, which is negatively charged electrons in a cloud surrounding a compact nucleus, which contains protons, which are positively charged. But objects can also have ions in them, such as sodium and chloride ions. And there can be molecular ions in or on objects, which also carry charge. So all of these charged particles are examples of charge carriers. The charge carriers in a material may or may not be fairly mobile. In other words, they may be able to move around, or maybe they can't. And how mobile they are determines whether a material is a conductor or an insulator. If the charge carriers are quite mobile, then the material will be a conductor. What is it that's happening when we touch the plastic rod to the metal sphere? Well, we know that the sphere ends up being negatively charged after it's been touched. And that's because some charge is transferred from the rod onto the sphere. Note that no new charge has been created. If you were to measure the charge on the plastic rod after touching it to the sphere, you would find that there's less. It would exert smaller electrical forces on things near it. But what's actually happening? What kind of charge carrier is being transferred? Because there are two possibilities. So one possibility is that when you touch the plastic rod to the metal sphere, because there are excess negative charges on the plastic rod, and we know that they repel each other, they will tend to push on each other and push some off of the rod onto the sphere. And so the rod loses some negative charges to the sphere. But that's not the only possibility. The other possibility is that when we touch the rod to the sphere, because the rod pulls on positive charges in the sphere, it could pull some positive charge off of the sphere onto the rod. Note that experimentally, these two situations are basically indistinguishable. Either way, the sphere ends up negatively charged, and the rod ends up less negatively charged than it was. In this case, we actually know that what happens is this one. But in fact, that's only because we know about what the charge carriers are in the metal. Most of the time, when a charge transfer like this happens, we can't determine which of these two things has happened without doing much more sophisticated experiments. The mechanism of charge transfer that we've just seen is actually the same as the mechanism of discharging. Suppose we have a top piece of tape, so it's positively charged, and you touch it with your finger. Then two things can happen. Either, because the tape is positive, it pulls on negative charges in your finger and pulls some of them into the tape, which partly or fully neutralizes the tape. But it's also possible that because the positive charges in the tape are repelling each other, some positive charge gets pushed out of the tape and into your finger. Either way, the tape becomes neutralized. I'm going to rub this plastic rod with wool to charge it and put it on a hanger so that it's free to rotate. And note that when I was rubbing it, I had to hold on to one end, and so there's actually only one end that's been rubbed. The other end I haven't rubbed at all. Then I'm going to rub a second rod, so it also has a rubbed end and an unrubbed end. Now, when I bring the rubbed ends together, they repel, as we would expect. They should have similar charge. However, the unrubbed ends seem to have absolutely no effect on each other. This rather simple observation tells us something important. We started with neutral plastic rods, and after charging them, all of the charge was on one end of each charge. That means that those ends repelled each other, as you would expect, since they were similar charges, and the other ends did not repel each other, which is why we know that all of the charge was at one end. And not only was it at one end where we had produced it, but it stayed there. And so this tells us that charge is not mobile in plastic. In other words, plastic is an insulator. Here are two ping pong balls covered with aluminum foil, and you can tell from the fact that they're hanging straight from their strings that they're not repelling or attracting each other, and I'm charging a plastic rod using wool. When I touch the rod to one of the balls, now the balls repel each other. Let's see that again in slow motion. Again, what does this tell us? Here's the negatively charged plastic rod, and here are the two metal spheres. As we'll see, the mobile charge carriers in metals are the negative ones, and so I'm only going to draw negative charges in this diagram. When we bring the rod in and touch it to the sphere, of course, as before, some charge carriers are transferred from the rod over to the sphere. However, because the sphere is a metal and a good conductor, these charge carriers are repelling each other and they're free to move, and so they will tend to spread out. This means that they travel all over the surface of the sphere, and in fact, they're going to make the jump to the adjacent sphere and spread out all over it as well. What we end up with is both spheres negatively charged, and the charges spread out evenly over them. Whether an object is an insulator or a conductor is a property of the materials it's made out of. Among solids, metals are conductors, such as the aluminum in the aluminum foil covering the ping pong ball. All other solids are insulators. Well, actually, that's kind of a lie. Pretty much all metals are good conductors to one extent or another, and there are a few non-metallic solids that are conductors, but for the most part, all other solids are insulators, at least at room temperature. Liquids are mostly insulators. So, for example, pure water is an insulator. However, you almost never come across actually pure water, and even very small amounts of dissolved salts in water make it a good conductor. Remember that you are basically a bag of salty water, and so that means you're a good conductor. Any liquid with dissolved salts will conduct well, because the dissolved salts are ions, which move around easily in the liquid. Gases are insulators, but if the molecules or atoms in the gas become ionized, the gas is now a plasma, and plasmas are very good conductors. That's what happens when a spark jumps through air from a charged object to another object. The most dramatic example of that is lightning. The Earth is very big, and it contains a lot of charge. And so if we have some charged object, and we connect it to the Earth with a good conductor, then if it's charged, it will tend to become neutral, because either these charges on this object are going to repel each other, and they're going to tend to flow down the connection into the ground, and because the Earth is so huge, it can take in an essentially infinite amount of charge and still remain essentially neutral. Alternatively, if these negative charges on this object are not mobile, then positive charge can be attracted up from the Earth into the object. Either way, this neutralizes the object. This process of connecting an object to the Earth so that it shares charge with the Earth is called grounding. When the object is already charged and there's nothing maintaining its charge, this will tend to neutralize it. But do not think that grounded things are always neutral. The key thing is that a grounded object is in connection with a huge reservoir of both positive and negative charges, and it can exchange charge with that reservoir easily. Let's have a question to see how well you're understanding things. So, as you've seen, many things can be charged by rubbing. The example we've seen is plastic rubbed with wool. Another example is glass rubbed with silk. But if you hold a piece of metal in your hand and rub it with anything, it doesn't matter what you rub it with, it will not become charged. So, here are three possible explanations for this. Choose which one of these you think is the most likely. So, if you're in the course, of course you'll be asked on Moodle to do this before you go on to the next part of the lecture. If you're not in the course, then you should really come up with an answer anyway to make sure that you're following along.